Hey, welcome back, donkeys, and let us jump right into some more gas work. And we want to learn today about gas stoichiometry. So, let us figure this out. Let's start here with this. Consider I have 528 liters of carbon monoxide gas at STP. How many moles of CO are present? What is STP? What do you think STP stands for? Well, let's go back to our notes and see if we can learn something about STP. Okay, so we have our gases and we have a definition and pressure and kinetic theory, and we have gas laws on here somewhere. And we're going to add to this, and we're going to put down here gas stoichiometry. Gas stoichiometry. Okay, so gas stoichiometry. Stoichiometry. I think we know where we're going with this. We're experts at stoichiometry, and so we should be fine with gas stoichiometry. First, though, we have something called the molar volume of a gas. Molar volume of gas. Good. And what does that mean? Well, it is what? The volume of 1 mole of gas. And this we usually refer to at a certain temperature and pressure. We say that it is 22.4 liters per mole. But now here's the important thing. At STP. What does STP stand for? What stands for standard temp and pressure. Cool. So that means at standard temp and pressure, every mole of any gas, it doesn't matter what gas I have, it can be O2, it can be CO, it can be NO. If they are at STP, their volume will be 22.4 liters per mole if I have 1 mole of those. Now, what is STP? T is 0 degrees Celsius, which we all know is 273.15 Kelvin, and P is 1 atmosphere. So if I have something, if I have any gas, let's see, what's your favorite gas? Krypton. If I have 1 mole of, let's see, we have 3 moles. I have 3 moles of krypton at 0 degrees Celsius and 1 atmosphere. How do I figure that out? Well, I have 3.00 moles of a gas times 22.4 liters per mole. If it's a gas, yeah, that's a gas. And it's at STP, yes, it's at STP, then I can use this conversion. So then I would take 3 times 22.4, 22.4 times 3, and I get 67.2 liters of gas. There we go. Now, does that matter if I change it from krypton to argon? Nope. How about if I change it to N2? Nope. If it's gas and I have 3 moles of it and it's at STP, the molar volume is always the same. Cool. I think we can answer our question now. Wow, we've done a lot, haven't we? Here we go. 578 liters of a gas at STP. Okay, if it's at STP, what do I know? That means I have 1 mole of that gas is equal to 22.4 liters. That is my equality, right? All right, so then what can I do? I have 1 mole over 22.4 liters. Hey, why did you set it up this way? Because they gave me liters this time. In the previous problem I showed you, they gave us moles. So we want to use the proper conversion factor, right? My liters cancel, and I'm left with moles. So I take 578 divided by 22.4, and my answer is 25.8 what? Moles. There we go. Excellent. Piece of cake. You guys do the next one. Are you ready? Well, I have 77.214 what? Milliliters. So what's the first thing I have to do? Convert that to liters. So I have 77.214 milliliters times 1 liter per 1,000 milliliters. Good. So my milliliters cancel. I'm left with liters. Yoink. Now what do I do? Well, it's at STP. That means I know that 1 mole of this stuff equals 22.4 liters. Okay, so I have 1 mole of my H2 over 22.4 liters of H2. And let's see, do my units cancel? Liters, liters, and I'm left with moles, so I just do the numbers. 77.214 divided by 1,000 times 1. Oops, divided by 22.4. I didn't have to multiply by 1, did I? 3.44. How many sig figs? I only have 3 sig figs here, so I can only use 3 sig figs. So 3.45 times 10 to the minus third. 1, 2, 3 moles. Let's check that out again. Make sure I didn't make a mistake. 77.214 divided by 1,000. Okay, that's cool. Divided by 22.4, and that's cool. Yep, that looks right to me. My units cancel. I'm left with 3.45 times 10 to the minus third moles of H2 gas. That's all there is with molar volume. Remember, molar volume, I have 22.4 liters per mole if it is at STP, where STP is 0 degrees Celsius and 1 atmosphere. Good. Moving on. Yikes! What's this? Looks like a reaction, and it is. If I have 163 milliliters, if 163 milliliters of H2 is collected at 35 degrees and a pressure of 2.35 atmospheres, how many grams of this stuff is produced? Okay, so I got some information on this, right? I have volume, I have pressure, and I have temperature. And I want to know some information on this. I want to know grams of that. And then I also want to know grams of that. Okay, so how am I going to do this? Well, this is nothing new to us. This is stoichiometry, right, guys and gals? Stoichiometry. So how do we handle gas stoichiometry? Well, in gas stoichiometry, notice what's stoichiometry in general? You know, I'd have a reaction, right? And here's gas, and here's gas, and here's gas. And the whole idea is I want to take, if I have a number here, I want to convert it to moles, and then I can go from moles of that to moles of this. How do I go from moles of H2 to moles of H2O? Well, I use a mole ratio, right? Mole ratio. And then how do I go from moles to grams, for instance? Let's say I started with grams. I would divide by molar mass here of H2, and I would multiply by the molar mass of H2O here, right? And so I could go from anywhere in my reaction to anywhere else as long as I was in what? I needed to be in moles, and I needed to use mole ratio, right? Well, how do things change if I have gases? Well, they don't really change much because if I have my reaction here and I have gases, that means I could, oops, sorry, it's not an, we don't want an equilibrium. There we go. What new tool do I have that I can use? Well, for gases, remember, for gases, not liquids or solids, but for gases, PV equals nRT. Where N is equal to what? Moles. So N is equal to PV over RT. Cool. So that means I don't have to go from grams to moles. That means what can they give me for a gas? Well, they can give me a gas, they can give me a volume, they can give me a pressure and a temperature, and what can I do? I can take a volume, pressure, and temperature and convert that to moles using N equals PV over RT. And then once I have moles of my H2, I could go anywhere to get moles of anything else using the stuff we know already, mole ratio, right? That's what we can do. And now I can go from moles to PV or T as long as they are gases. If they're not gases, I can only go from moles to grams or moles to particles. Got it? Okay, let's see it in action. It's really quite simple since you have already mastered stoichiometry. Okay, what do we start with? I start with, I have a volume for my hydrogen. I have a temperature for my hydrogen, and I have a pressure for my hydrogen, right? Let's clean up this a little bit. It's kind of messy, isn't it? So let's get my volume for my hydrogen is equal to 163 milliliters, but if I'm going to use PV equals nRT, I need to convert that to liters. So that's equal to 0.163 liters. What's my temp? My temp is 35 Celsius, but if I'm going to use PV equals nRT, I need to convert that to Kelvin. So we want to take 35, and 35 looks to me like, what is that? That's 308.15. Now the 15 is not significant, is it? No, it's not. Kelvin, you guys buy that? If I add 35 here, I get 803. Yeah, it looks like 308.15. And what is my P? My P is equal to 2.35 atmospheres, right? So I can get moles of H2. How? Moles of H2 in is equal to PV over RT. What's my P? 2.35 atmospheres. What's my V? 0.163 liters. What's my R? 0.08206 liter atmospheres per mole Kelvin. Yeah, we want to keep using our units so we remember, so we can check to make sure our units are correct. Okay, Kelvin cancels, atmospheres cancel, liters cancel, and I get 1 over moles, which is equal to moles. Okay, here we go. 2.35 times 0.163 divided by 0.08206 divided by 3. Oiks, I made a mistake. Ay, ay, ay. 2.35. Gotta start all over. Times 0.163 divided by 0.08206 divided by 308.15. Man, I hope you did this right. And I get 1.51. How many sig figs? 3, but we want to carry one more. 1.514 times 10 to the minus 2. 2 moles of H2. Let's check that again. Make sure we didn't make a mistake. 2.35 times 0.163 divided by 0.08206. Good. Divided by 308.15. Good. That's correct. So that's going to be moles of hydrogen. Excellent. Is that my question? No. How many grams of KNO3? So I need to go from moles of hydrogen to moles of KNO3. And how am I going to do that? Mole ratio. I have 1 mole of hydrogen to 2 moles of KNO3, right? So let's come over here. We're going to get moles of potassium nitrate. That's equal to 1.514 times 10 to the minus 2 moles of hydrogen times 2 moles of potassium nitrate per 1 mole of hydrogen. Did I do that right? Let's go back and check. 1 mole of hydrogen, 2, yeah, cool. So what that equals what? Times 2, and I get 3.029 times 10 to the minus 2 moles of potassium nitrate. But what do they want? They want grams. So how do I get grams of potassium nitrate? Grams of KNO3 is equal to 3.029 times 10 to the minus 2 moles of KNO3 times what? Okay, let's look at our periodic table. What's my potassium? Potassium is 39.10. We'll go with 39.10. Yipes. Yipes. 39.10 plus nitrogen. Nitrogen 14.01 plus 14.01 plus, I'm glad I know oxygen is 16.00. And that is grams per 1 mole of KNO3. All right, let's do the numbers. Times quantity, 39.1 plus 14.01 plus 48, close, equals, woohoo! And my answer is 3.06 grams of KNO3. There we go. Now, they also wanted to know what? How many grams of potassium were reacted? piece of cake, right? I know how many moles of hydrogen. I'm going to go moles. Let's clean this up a little bit. Zoink, 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 zoink. I knew how many moles of hydrogen, and so I can use stoichiometry to go from moles of hydrogen to moles of K, right? So let's go down here. Where's my moles of hydrogen? Moles of H2 is what? Where's moles of H2? Equals 1.514 times 10 to the minus 2. Okay, so then moles of K equals 1.514 times 10 to the minus 2 moles of H2 times 2 moles of K per 1 mole of H2, right? When we go back and check, 1 mole of H2, 2 moles of K. Yep. Zoink. Good. So that is equal to 1.514 times 10 to the minus 2 times 2 equals 3.028 in this case, because we rounded, times 10 to the minus 2 moles of K, right? And then I want to get grams of K, so that's going to be equal to 3.028 times 10 to the minus 2 moles of K times what? 39.10 grams of K per 1 mole of K. And that equals what? Times 39.1. And I get 1.18 grams of K. All right. Pretty cool. You guys do this one, and we're almost done. Bring me back when you're ready. Well, what do we start with? I have 25 grams of K. We're reacted with excess nitric acid, so we don't have to worry about it. And we want to know what volume of H we would get at these conditions. Okay, so first thing we want are moles of K. Moles of K are 25.0 grams times 1 mole of K per 39.1 grams of K. Yeah, I remember that from the last question. 25 divided by 39.1, and I get 0.6393 moles of K. Well, where do I want to go? Well, I have questions about H2, so I want to connect potassium to hydrogen. So how do I get moles of hydrogen? Well, moles of hydrogen are going to be equal to 0.6393 moles of K and times what? 1 mole of H2 over 2 moles of K. That's my mole ratio, right? Moles of K cancel, and so I have to divide that by 2, and I get 0.3196 moles of H2. Good. Now what else do they give me? They give me my pressure of H2, which is equal to 725 millimeters of mercury, but I need that in what? If I'm going to use PV equals nRT, that has to be in atmospheres. So I need 1 atmosphere per 760 torr. Okay, so let's take 725 divided by 760, and I get 0.9539 atmospheres. Good. What else do they give me? They give me 300K. Okay, good. That's already set. Then we can do it. So we know that PV equals nRT. What are we solving for? We're solving for what? Volume. We want to have volume. By the way, can I even use this? Why can I use this? Because hydrogen is a gas. If I have a gas, I can use PV equals nRT. If I don't have a gas, I cannot. So volume is equal to nRT over P. N we said is 0.3196. R we know well, 0.08206 liter atmospheres per mole Kelvin. Temperature is 300 K. Yeah, I like it when they give it to me in K. 300 K. and my pressure is 0.9539 atmospheres. Let's run the numbers. Okay, 0.3196 times, I put in the wrong number already, 0.3196 times 0.08206 times 300 divided by 0.9539, and wunderbar! We have 8.25 liters of hydrogen gas would be created. Excellent. Let's run the numbers just to make sure you didn't make a mistake. 0.3196 times 0.08206 times 300 divided by 0.9539, and I confirm that. Good. Excellent, ladies and gentlemen. Okay, we're almost done. We have one thing left to do, and then we are done with the chapter. So I'm going to go a little long today, and we want to go through this. Consider 4 moles of neon gas at 10 degrees Kelvin and 1,000 degrees, 1,000 atmospheres. Wow, that's a lot of pressure. Kind of what I feel right now, trying to get this done on time. Well, before the time expires and I expire. Would you expect this gas to behave ideally like you, my wonderful students, are all acting at this moment ideally? Yes. Well, ideally, we've talked about a little bit. We said there's something called ideal gases. Let me get rid of some of this. Zoink. Voila. Don't you love how I can just make the world disappear? Let's talk about ideal versus non-ideal gases. Well, very simple. An ideal gas obeys, I guess I would say, the assumptions of the kinetic theory, right? And real quickly, what are those again? I have a large number of tiny particles far away from each other. I'm not going to write these all down. Large number of tiny particles far away from each other relative to their size. These particles are in continuous, rapid, random motion, right? There are no forces of attraction between these particles. When these particles collide, those collisions are elastic, and then the temperature reflects the average kinetic energy of the particles. Okay, so an ideal gas obeys those assumptions, which would mean a non-ideal gas doesn't. And now the question is, when do gases not behave ideally? And if that means not behave ideally, that means when do they behave like real gases? When do they act like real gases? Okay, under 2 conditions. Well, number 1, under high pressure. When they're at high pressure, that means my gas particles are very close together. And when they're very close together, that means forces of attraction become significant. Not only that, but also their volume, the volume of a particle, becomes significant. Okay, so that's the first situation under which gases do not behave ideally. In addition to that, or with that, the other is and at very low temp. So when do things act like a real gas? At high pressure and at low temp. Why at low temp? Hey, that means they have very low velocities, and once again, at low velocities, they get close to each other, and forces of attraction become significant. Okay, that's all I really want you to know. So, an ideal gas obeys these assumptions of kinetic theory. Real gases don't. When do gases act? When are gases most real? At high pressure and at low temperature. Got it? So let's answer our question, and then we are done. What do I have here? I have a high pressure, and I have a low temp. So would we expect this to behave ideally? No. We expect it to behave like a real gas, and that is it. So you guys can, now that we're done with gases, you can go out and you can behave really, or you could behave ideally. It's whatever you want to do. Okay, I'm done. I'll catch you next time with a new unit. See ya.